Isaac, he okay, let me have my there. Okay, so he studied at the Technische Universität in Darmstadt, Germany. Then he did his PhD at the Ludwig Maximilian University in Munich using ROSAT data of very nice memory for many of us. Then he joined ESA, then called he then joined what is now ESAC, that then was called VILSPA, as resident astronomer in 1994. Then in 1997, he became astronomer for the XMM-Newton Science Operating Center. And since 2004, he's been the XMM-Newton project scientist already on what is now called ESAC. And it's for me a pleasure to present him and to introduce his talk about the scientific strategy of XMM-Newton. So Norbert, whenever you can.
Okay. Good afternoon, ladies and gentlemen. It's a great pleasure to give you this talk about scientific strategy. It is several things we try to get out in this year that have brought out last year, who try to get a larger view of the XMM development and the scientific strategy. Here a short agenda. The main point is basically this usage, users, discovery space, and at the end the pre-review. XMM-Newton is the only ESA mission which was twice subject to a review in Nature, both together with Chandra. And I think these two reviews in Nature underline the high scientific impact recognized by the wide scientific community of these two missions. And it was surely the synergy of the two, the special resolution and the high effective area, which makes this tandem so successful. Here a picture from the construction. I think it's still the largest scientific satellite built in Europe. We have 3 mirror modules. This was specially developed at this time for XMM-Newton. Volta 1, each mirror has 58 gold-coated nested mirrors. Here are the instruments. We have here the mirrors, and we have in 2 reflection gratings, which gives us high resolution for the soft X-rays. The 2 instruments, the 0 order basically go to the MOS cameras. Then we have 1 X-ray telescope, which is not disturbed, which goes directly to the PN camera. And in addition, we have an optical monitor. This shows all the sleuths performed by XMM. Here are all the pointings. And basically, this summarizes XMM. We have the 3 mirror modules. We have still, say, the highest effective collecting area at the iron line. We have 6 simultaneously observing instruments, 3 CCD cameras, 2 spectrometer, and the optical sync. Now going more to the policy, the ESA mission extension is a schemata from 3 + 3 years, where we have 3 years approved up to 26, and we have a tentative approval from 27, 28, 29, and this year, next year, we have to ask basically for approval of this time and the next extension. This mission extension forces always an evaluation of the performed science. It forces us to formulate new scientific goals and also to revise in some way our strategy. And I think even if it's a big burden, such an extension exercise, it's also a good thing for the mission to keep it healthy and at a long time on a good track. Most important is the scientific output. For this, we download all referred paper from RDS mentioned in XMM-Newton. Then we classify them. Most important, the blue, which uses the data, catalogs, numerical prediction, description, and the red one then uses our products, be it the catalog, be it pipeline products. And this one we count here. We have then such a gray area which uses products produced from other sites or from papers. If someone takes the image from what of XMM-Newton taken with XMM-Newton in another paper, then this comes in the gray one. Also these are the papers we are really counting, and you see this goes up and goes then slowly up, and then in the last 3 years, even much more, now with over 470 in last year, referate papers using in any way XMM-Newton data. And then in addition here, the papers in Science and Nature journals family, and we see that it was quite low up to 2012, and then it was going up, and then we keep here a high level, where about always of 3 to 4 are mainly dominated as XMM essential from them. Now, looking from the papers to the usage, how much of the time is used, and this for the day, this is a (99, 97%). Defines dedicated articles as others, and the black one are general catalogs. And even there, over 90% normally is here on a long scale used in dedicated paper. Many data is used several times. Here in the first year, 29 times, in the second 32 times, and then dividing by the number, the average years, the average usage per year of this data. This means observations taken in the first year still are reused a factor 1.2 times per year. And this is an extremely high usage. And this, if you compare it with a typical optical observatory from the ACO, which is in Europe the ground pattern from the ESA, there is such a good usage is in 60% region, where we come here easily over the 80. Also very interesting, if we look only to the C targets, still there is a very high usage. This at first is a little bit misleading because we had some few C targets or no C targets, but then it's still a very, very high usage, also quite different from ground observatories. The second very important point is an announcement of opportunities, the number of proposals reflecting the interest in the community of XMM-Newton. It was very high in the two first one. I think this was too high, but then it was then going down here basically. And from 2012 on, it's more or less constant. But the oversubscription then at the same time here is much more later, always between 6 and 7 normally. We have then since 3 times the multi-year heritage program, which we call every 3 years. This is a very small number, but the oversubscription is then comparable with the normal programs. Also, to summarize here, more than 400 reference papers, more than 90% of the observer data is published. Most data is used multiple times. Some 470 proposals with a high oversubscription factor, typically between 6 and 7. Now let us have a look to the XMM-Newton community, and this again is to be published by Jan Uwe, hopefully very soon.
Norbert, excuse me a second. I think that your slides are stuck. Can you get out and come in again from the presentation mode?
Are you out of the presentation mode?
I can only see usage. I haven't seen the usage slide for a few minutes now. And it's all I see on the screen now. Can you stop sharing and share again? Right.
Are you sharing again?
Okay. Oh, now I see the right. So can you go into presentation mode? Just move the slide before going into presentation mode, just in case. Okay.
This was a usage.
Yeah, this is usage. Okay, now it's okay.
Okay.
Yeah, I don't think we saw this slide. We heard you, but I don't think we saw this slide.
Sorry. Then I repeat here. So we have here the number of proposals for each announcement of a community. At the beginning, extremely high numbers, which I think was too high. It was then going down up to 2012, and from then it's quite constant. The oversubscription was in some way more constant, basically, and is now a long time between 6 and 7 here. We have sensible year heritage programs in 3 years, where we give half a year of A and B time out, which is called every 3 years. And here's a very small number of proposals, but still the oversubscription here in the frame of the normal oversubscription of the programs. Then the message is more than 400 refereed papers, more than 90% of the observed data is published, most data are used multiple times, some 470 proposals, and a permanent high oversubscription factor of the proposals from 6 to 7. Now, coming to the scientific community, this is again from Jan Uwe's paper to be published hopefully soon. He takes basically in this small red dot line is all papers per year. And the red line gives the number of first authors per year, also people who have published for a paper, and very few have published 2 papers, therefore this number is always smaller than the other one. The black symbols, this shows a number of people publishing the first time an XMM-Newton paper. And you see this goes here up to 2004. And from this it is quite constant. So we have permanently new authors, some 130 people writing every year for the first time their data, paper with XMM-Newton data. And now the blue line is the opposite, as people who write for the last time an XMM-Newton paper. Clearly, some people only in the first year, and this follows here the black line with some delay. And from 2010 onwards, it is ungefähr the same number as the people writing new authors. And then you see in the last year here, clearly everybody has written his last paper with XMM-Newton data. But now, the fantastic thing is, given the constant here, means we have a constant community, and this excess integrated gives you simply the total number, because there are people who work on paper but have not published so. And this allows us basically to conclude we have 460 lead scientists publishing as first authors paper using XMM-Newton data. We made them the same study for all authors, including the co-authors, and this gives us then integrating the access here. 4,002 scientists are involved in publishing XMM-Newton data in refereed journals. Now, one other thing, again from Jan Uwe, how long do people publish? Also he takes out the difference between the last paper and the first paper, and then he gives for every author a number. And we see that 51% of the people only write one paper, say PhD, maybe a master, which results in one paper. Then we have here 25% in such a range here up to 6 years activity. And then we have a tail here from the long time working people with XMM-Newton paper. These are only 24%. Very similar for people who are with the co-authors taking all. And this describes how the community is how involved. So we have very likely this and this education, a very, very much usage from education things from XMM-Newton data, and in principle a relative small community or a smaller community for people working on longer times. As a constant number of scientists since 2010 working with XMM-Newton data, 4,200 scientists about, 560 lead, and 50% one time with XMM-Newton, 25 up to 6 years, and 25 are the core stuff. Let us now go to discovery space. And I think you must realize discovery space is restricted if you have a mission like XMM-Newton. And the main point is that the quality of the spectra, which is given by the number of photons. We know all photons follow the Poisson statistic. This means the signal to noise, and this means the signal to noise increases with the observing time to the square. An example, if you have an observation with 10 kiloseconds, assume now you find something interesting, you want to study it in more detail. To get a factor 2 in signal to noise, you need 40 kiloseconds. Say now you want to have the width of the line, then you want to lose the asymmetry, 160 kiloseconds, and the next escalation is 540. But this kiloseconds you should compare with the time which typically is available for a panel, and these are 400 to some 800 kiloseconds. This means we run here very quickly out of the signal to noise if we want to study things more intensive. If you look to surveys, for the surveys, the important point is a number of sources. A number of sources goes according to the area. But if you want to say you have a sample of 100, if you want to get a signal of noise of any effect, to double it, it goes again with the area to the squared. This means again with the time to the squared. Other possibility is to look to other sources in the sky. And I have here more some 2 samples. One is the brightest optical stars nearby. We have one very nearby. Then the second, the factor 2 already lower. And then here comes then the rest. But you see, you have one source and all others are factor 5, 7 below in the flux. Similar, if you take the Piccinocchi sample, one very bright, then there are a few, but then it is immediately to come to lower fluxes. And this we see also, we have less and less duplication within the review process. But if you take the statistical argument plus this distribution of the sources, and you can rescale the sources of every source class, it's a subclass, then you see that after some 7 years, a new facility has explored its discovery space. It sounds now a little bit strange, but look at it maybe from our other side. If you take the 7 years observation and you want to do it with a factor 2 improvement in signal to noise, you would need 21 years. And you see 21 years is complete any schedule for our human academic lifetime. And therefore, I think this 7 is a natural scaling which simply reflects our human limited lifetime. Now, what is a normal consequence of this? You have here from IOE the publication. This is exactly analyzed as I analyzed the XMM-Newton. And you see here, this is normal. You have this within 5 years going up, and then you have this exponential going down. Here's this whole, I come later. And IOE you can well compare because it had similar, some way comparable for the UV, what is XMM for the X-ray. Now, what to do if you want to continue after 7 years? One point would be new instrumentation. I think VLT development, VLTI with Gravitas is fantastic, but quite limited for current generation of spacecrafts. We have it in HST with a service mission, I also wanted to promote it for ASA to do it robotically, but this was not so well received. For XMM-Newton, we have some 40% signal-to-noise potential from the cross-calibration of the instrument, which we will use in the next step. But here I think it's clear we cannot go. If you look to universities, they often then go from research facility to education. High student numbers and the shortage of institute-owned facilities in Europe in principle, but it is problematic for mission extension. Also, XMM is already highly overlapping the scientific use with education. But a purely educational mission would be, I assume, very hard to justify. Another thing which we studied is a change of a scientific goal. We studied this for technical reasons. Would it be possible, would it make sense to use XMM as a survey facilities? And this looked very, very bad. It becomes extremely inefficient if we go away from pointing these observations from large areas. This is really not constructed for X. Another way is to expand the scientific discovery space. And this was the way I think we were going. And this is always development out of small start points to put your policy in the time correct, finally to expand it. And this was also IOE doing. When IOE had here this poor IOE phase, and since they had this joint observation with ROSAT and other facilities, and this boosted here the publications again. And I think at XMM we were in principle doing the same. Expanding a scientific discovery space, the first point is also large programs. They allow to basically to get some viewpoint, a small looking to science in principle for the next generation of missions. The rules and procedures for the ODAC were several adapted to follow the changing requirements and to allow the programs where the ideas were out in the community, allow them to propose and to follow it. We have now two types of programs, one more than 300 kiloseconds. They have exactly the same oversubscriptions and normal programs. Typically, some 45% of the A and B time we give to these large programs, but normally, basically all large programs, you cannot allocate C time. And this makes a big difference. And also most large programs you have to accept completely. And this makes only very, very few, really this oversubscription from 6 to 7, you see then with this effect for the large programs. Science examples, long observations to study variability. I think the spin and mass determination of supermassive black holes is an example. Deep spectra of weak sources, the detection of the wind, and many samples. And then we have the multi-year heritage program, more than 2 megaseconds. We can only offer it every 3 years, and it's performed over 3 years. And so far, only two programs were accepted. Science was an extragalactic survey of 4.5 megasecond, the galactic center region, samples of Planck clusters and high redshift clusters, high redshift quasars, and in the last time then this Euclid field. And here now this evolution in the statistic. You see, we started with one large program with AO1, which was not foreseen by OTAC. We changed then the rules and so on after some oscillation. And finally, this was building up during the first 9 years. And from here, it is constant. We tried these very large programs, but we changed them to this multi-year heritage program, which is simply much smoother in the OTAC process. And these programs then observed over 3 years. The same thing here in the time, basically, it goes up to after 10 years, then it is constant, and here's this yellow one distributed over 3 years. These images are from Pedro and the others from Pedro and Laura, and we hope also to get this out in a publication. The next point were joint program. We have joint programs from radio to TV. We have radio NRO, JWST, VLD, HST, Swift, Chandra, Newstar, Integral, has Magic. I hope we have a next year XMM also. Most successful if the two facilities allow to address the same science. I have it a plan, even if we had no joint program here, but there was an enormous amount of follow-up because the Zayas-Sedovich effect in the clusters and the X-ray is basically the same gas which they measure and measure it in different way, allow to give light to different aspects. HST absorbing winds and outflows in HENs and binaries. Here is often the idea, how does the X-ray wind, the X-ray absorption line correspond in the UV. Then induced us this 6.4 keV line as a diagnostic for these compact objects. And here that is very important, the strict simultaneous observations. This was an enormous amount of time we spent with this, and then it got very good results. And then Hess and Magic, the identification and mechanism of TeV emitters. This requires also partly simultaneously. Looking to the evolution now, it is basically we had it from the beginning, but this was very, very low up to 2010. And then from 2011 up to 2017 something, it goes here up, and then it stabilizes here by this high number. And here's the same in the time, very low up to 2010, and from 2010 here from 2015 up, and then stable. And you see here also very important was a new star in the whole story. And here I think this is chrism in the time already, which we see here. Finally, targets of opportunities. Targets of opportunities were not foreseen during the planning and development of XMM-Newton. The baseline was 4 weeks scheduling. And in AO1, we introduced this triggered observation that in the minimum people, if they had a target, we wanted to observe at certain states, that this was possible. And then was very nice. The director of science, and this was Professor Bonnet at this time, was asked in a press conference in relation to XMM-Newton. I don't remember what it exactly was, end of commissioning or something. He was asked basically in a public press conference if XMM-Newton would allow anticipated TO observations. He said naturally he would do it. And with answering this question in public basically was the permission and to convince management that we should do it. This then we got later as anticipated TOs. Important was a change in the rules that an OTAC chairperson, if she or he approves a TO, that we can observe it without coming in these time limits. And this made the way free really to put us on the TO track, which is now so important. It is important for these things always to have procedures in place in time before they ask for. And it's now supporting this increased weight of the time domain. And we have the beginning was gamma ray burst, Pepper-Sachs, Swift, Erosita. Now, then optical surveys, very important now, and now Einstein, and in future LSST. And now again, to the number of TOs, you see here all the TOs, it was up to 2015-20, and then it goes here really up. With 120, this means we have every third day, and TO being anticipated or the unanticipated, and here now this enormous time we put into this. Looking to it overall here again, it is on the left side the number of observation, on the right the time, but it shows basically the same. You have first the large programs in the first 10 years, then the joint observation from 10 to 17, and now the TOs coming up. And this allowed to keep XMM-Newton always on the forefront and always with high impact journals. Now comparing now these two light curves from IOE and with XMM, and we could here keep it basically as the 5 years to go up, and then we could keep it here overall increasing number of publications. Also we have 3 phases of the extension of the discovery space, extended observing time, then joint programs, then target of opportunities. Before going to the OTAC, was some things with conflict of interests. Assuming we have here this, now this D and A can mean proposals, can be PI, as it depends a little bit from view graph. We have sent the people in the OTAC, and in the OTAC we have a panel with now, as we have it, 5 members. Now, assuming now this panel member has a conflict of interest, we put him out of the panel meeting, the conflict solved. But we have a major bias. See, but people react completely different. But this is enormous variations that people don't care, other people are very sensitive. If you put a PI of a proposal here out, I think you have normally a massive bias on this panel decision. If this is now, say, the conflict here is that the co-I of the proposal has the same affiliation, then the bias is very low. But the point is, moving someone out implies a bias. If you have someone in the OTAC, the panel, clearly no conflict, he is not in the panel discussion, but a bias. Simply the fact that the people know that someone is in the OTAC can make a bias. Someone from outside, this is no conflict. But, and this is very interesting, if there are 2 people from the same community, then you get a bias. Because the people, some people, not all, it's completely different, but there are people who become reluctant to speak about, open about this proposal if there is someone from the same community. Same target, clear we get out, this is clear, no conflict, but if you have the same science, you don't flag it normally as a conflict. But if you have a merging of the results from different panels, then you get a bias because the people know that there is a competing proposal of their own, which maybe in the merging has a negative effect. And finally, now, assuming these are proposals, the problem of a small number of small areas. If you have, say, AGN proposal, have them one different one, or the 2 flash from stars, and have them one solar system, it is very difficult. This can go in a positive direction. I would say the solar system in overall were very successful compared to what they would have much more proposals. But in general, such small areas is very, very difficult to give them a fair chance. Therefore, you should avoid always the small thing. And what we basically implemented over the time, we improved step by step. I come basically an OTAC where the panel do not know each other, and I give you the details to come over it. The conflicts of interest, easy to recognize, straightforward, but the bias of very hard to recognize and difficult. We have taken bottom-up approach, systematic elimination of the biases by the procedures, and this resulted in a distributed peer review. Now, this is published by Arvin here. It is in a book, a chapter in a book, but it is now also an Astro PH, where we basically analyze the results of our peer review. I don't want to give too much to this article. I would more explain what is behind how we reached it. This is the distribution of gender as the function of the year since PhD. And you see here we have a high fraction of females up to 7 years after PhD, and then it becomes very flat. What we want to do with the peer review, we want to distribute the observing time and what we want, we give this observing time out, but we want to maximize the publication of high impact results. We need a deep trust in the community, that is the process and the fairness. Establish a program which is convincing for the community and ensures a flow of publication. But we need also a program which is convincing for the founding structures, because we need the emission extension in 3 years. We want to include the community in the process, and we want to establish support for it, and building a connection with the community, especially small countries, new member states. This is a way to connect to such people which are difficult to reach in other ways. The peer review should not be a burden. It should be something positive. And in principle, I think in general, the XMM-Newton is maybe not a burden, is too much. But normally, if people ask a second time, they agree and are often happy to do it. It's a different question if they are, because of conflicts, cannot do it. But this is a different question. Now, some background in AO1, we had a classical setup, 1 panel per scientific category, 7 categories, between 5 and 9 members. All conflicts in the panel were solved by people going out of the room. We had the panel meetings on different dates. The point was simply we had only 2 people to support the meeting, which we thought at this time would be important. And we had people from almost all member states from ESA, and this we try still to keep. In this review experience, I saw brightest light and darkest shadow, but we changed immediately the setup after it. In AO2, we were going with 15 panel with 3 panel members only. This was a recommendation from the users group. And this was also changed. Also, the 15 panels allowed us to get rid of these main conflicts of co-I, PI in the panel. This, I think, was a very important step. The 3 panel members work normally good, but it can run very bad if there are people who cannot work together. With 5, we had never such a problem again. And later, basically, we have permanently improved the process based on personal experience on the chairperson meeting where the large programs are discussed and from other comments. What we are doing is we have 2 or more panels per scientific category. With this, we can eliminate the major direct conflicts of interests. Each panel of 5 members from different communities to avoid this bias from the same community. Each panel meets on different dates and places. No bias from other panel members. The panel members do not know the members of the other panels. Again, no bias from panel members. Each panel has a defined and fixed budget of observing time. And this allows to get this bias out from competing research interests. And if possible, panel members from every ESA member state. The majority of panel members are selected from PIs and COAs of previous AO. Also today, the large majority from panel members are the people who are proposing XMM-Newton proposals. And I think this is correct. Why should someone else judge about them? What is the outcome? We have normally in the panels a sufficient high number of proposals, which allows to identify really the best proposals. Keep in mind the high oversubscription, and also to have the small areas a little bit covered, that there are 2, 3 proposals to compare with. sufficient expertise for discussion and identify hidden visibility problems. This is a very, very important thing to get these targets out, which give no flux, which you cannot do from the beginning. Die Gender-Statistik equals the outcome from the double anonymous. We have for men to female as a ratio of 1.1, but this gets also the double anonymous. The relative success rate changed from AO and AO. This means we have AO where the females have a higher success rate than the men. The acceptance rate from young proposer is 37% for people for a PhD. And this is something also which was only reached after double anonymous for other missions. We have, therefore, I think, no bias against the age. We have no language bias, which is also a big problem in some. Also we see here the UK, here Italy, Germany, France. The UK as native English speaker are not no better than the others. And I think it's very important. We keep the original research ideas connected with a PI name, and this is enormous push for career for young scientists, even if the proposal is not successful. If you have original idea and discuss it in a panel, I think this is the best what you can do in your career. These are these different rates. This is again from the paper from Arvin here, and here now been for PhD years, men and female success rate. Here, I think there is a problem with elder females, and I think the problem is that they are partly too much asked to do other tasks. And here again, the total here, and here's the 37%. And this is something we have for the data for 25 years, and not only in the last 2. Now, and here is the overall statistic, and here's this important number in comparison to HST, which is 1.09 after double anonymous. Also, the takeaway for a quarter of a century, XMM-Newton review has achieved gender and age acceptance value that other major observatories have only reached in recent years. Paper versus proposals. This I thought I comment on. I remember this, but I don't remember who told it something. As anyone can write a paper, but convincing a panel of peers of your scientific idea is another matter entirely. And if you look in the archive, you have enormous amount of observations. Even if they are published, there are many aspects you can write a paper on it. But the problem is people must become active, must propose new science. And you see this is first, this enormous amount is only one paper, but even here, I think there are many people hidden who would like to start a career, but don't start. And here it's very important that you go and start to convince panels about your scientific ideas. And these ideas is highly appreciated from the people at the end. It is to convince these people, because here are the positions. And you have this high oversubscription, but you see here for these large programs, if I see correctly, so far every person, and especially the young person with such large programs, they all at the end had still a position in science. And clearly is this old very important people like Fabian, Hasinger, Böhringer, they broke it, they established it, but now it's completely open. These are new people, and these are even basically students long before the PhD who get it. I think I stop here. My time is over. I have still the XMM-Newton model, which is basically assuming a small European university where people are not permanently, and our aim is basically to give the principal investigators a fair and reasonable opportunity to publish their XMM-Newton data. Okay. I thank you for your attention and time.
Thank you, Norbert. Sorry for the small technical problem at the beginning. So are there any questions from the panelists or attendees? I have a question / comment. When you said that more than 90% of the data are used, I guess most of that is from the archive.
No, we have enormous amount from the data. Also it is. We had these catalog papers treated separately.
No, I don't mean the catalog paper. What I mean is that.
Can you? No. Yes, clearly they are mostly from the archive.
Okay, so the people asking for the time, they are not necessarily the ones publishing the paper.
Yes, definitely.
From the archive.
No, okay. But if you look here, 29 times published, 32 times in the first years, the people have not written 32 papers about it.
Yeah, so I think that highlights the importance of having a well-thought archival facility even before launching the mission.
Yeah, you should start to have it, but you need it after launch.
Yeah, but I think it's important for Athena to keep that in mind and have a proper facility.
You need the archive, but I think important is that people even more important are the products, that people can directly use it. But you have to, if you have to coordinate, you have to be able to find what is there. But then I think it's important that people can pick it up and can use it.
Yeah, level 2 data, process data, yeah. Okay. There, Nanda, please.
Yes, thank you very much, Norbert. Very interesting. I have a question. Given your experience with XMM and the nice thing you mentioned about TOs, that they were actually not thought about well in advance, but they could be implemented. So seeing it from a NewAthena perspective, is there anything, since now we're looking for adoption, so we have some little time, is there anything that you think we should not underestimate?
Yes. Also, it was not that TOs were unknown when XMM was planned. If I am too young for this, but if I understand backwards correctly, they were simply dropped or not put in to keep the budget low. And we implemented it late, and this costed enormous amount of work, and it still costs. And even our possibilities are restricted. Also, it starts with the instruments. Do you have an instrument which you keep, say, start observation, or have you to select the modes? How quickly you can stop an instrument? Can you stop it, go to the next target, or to have you with the OM for us to wait that the observation is finished? Also, it starts even in the instruments, in the satellite, and also on the ground software. You have this web page for TOs, which we made separately from all our other systems, and we have manually to implement it. If we would have planned this from the beginning, you would have a complete system like the Swift. You get it on your mobile phone and say go, and we have enormous work to get it in. Also, this is something which should be from the very beginning in to ensure that it can be very smoothly implemented. And it is not a matter what you observe. This is not important. The question is that you have a quick reaction time. And with a minimal work, if we would have one, we have to check the optical fluxes. If you have an instrument which adapts by itself, you can simply go.
Thank you.
Ciro.
Good afternoon, everyone. Can you hear me?
Yes. Yes.
So first of all, thank you, Norbert, for this comprehensive and interesting review. Basically, one question. Nowadays, things are getting complicated in terms of data managing, and in the future, it's going to be nearly impossible to do everything on our own laptop. So my wondering if there's any chance that the future we are going is the one where basically we go online, we search for a source, and we can get the data in a way that we can already analyze it, and without the need to update the calibration files, install all the data reduction software and stuff like that. This is for XMM, which already provides some sort of level 1 data. But for missions like Athena, which are going to be way more complicated, it sounds like something we're really going to need. Thank you.
This is completely the opposite. It's today much easier than it was in the past. I was with Rosat in the survey. There was the computer so restricted that you could not produce this data. You had to accumulate the data for a small area on request only. And this was an enormous problem for the computers. And now you people have it on a stick, the Rosat data. Now with XMM-Newton, this data was so out of scale what astronomical data had before, that we developed the SAS not because we wanted to develop the SAS. The point was that the available software could not handle our data files. Rosat used just this EXAS or the MIDAS thing. It could not handle such big files. Therefore, the SAS was developed. And the reason why we have all this calibration and things was very clear. This in the concept, one clearly, ideally, you process the data and have in the minimum the calibrated event files in the archive. But it was clear for us that this processing is an enormous problem at this time, and that the calibration change. And you don't want to wait then 2 years for a new calibration of the archive. And therefore, we made all these procedures. And if you look basically how the SAS and the archive was built up, you see that we need several years to get good pipeline products in. These things which you say reflect that the computers were not able to do it in the past. And therefore, I know it, you're here, they come with Gaia and then no, I click. In 10 years, this data are small. This is a natural point. You have always the mission on the absolute limit, and you make compromises to get it at all in. And in my opinion, this data transfer is already today restricted. And it is vulnerable against attacks from enemies. I would not expect that it, I am not so convinced that there is a way. But the principal problem you have with all satellite missions, when you build them, the top of these satellites has much more data as you think you can cope with. But think always in 10 years, the world looks completely different. Sorry if it's not what you wanted to hear.
Oh yeah, well, it's fine. I think missions like LOFAR are very complicated. There is some sort of pre-reduction. Once Athena will be launched, the XFU, for instance, will be so complex, the data will be huge that not everyone can kind of reduce it. So I was wondering if we can forecast something like a platform online. But yeah, it's okay. I get your point. Thank you.
Also, my experience is the software is much more changing than the hardware. The hardware you cannot change. In XMM, it's an enormous big problem to keep our systems running because the computers run out of maintenance. The software, these things are not any longer supported. We spend enormous amount to keep the mission running because of the software changing.
Okay, I think we're going to allow our last question because we are reaching the hour. So, Peter, you should be able to talk now.
Okay. Actually, more a comment to the previous exchange. So the truth is that we're trying to set up something. We would be able to connect via browser, and maybe not exactly what you were asking for, but to make it easier, let's say, to access data. And we have discussions on what other kinds of data products might be produced as part of the standard kind of processing. Yeah, but this is all still things which maybe, so we're looking into this also within certain thinking that maybe some of these discussions may benefit NewAthena at some stage. Yeah, high-level data products, data cubes, and so on. But it's early to say how well that works and how much you'll really be able to do. Because I mean, I've been burned too often by people thinking they know exactly what I need. Yeah. And and on the other hand, it's true that it's always starting almost at zero is also getting a bit painful sometimes. So, I mean, it's fine. I don't really do it much more for XMM-Newton nowadays, but try to do it for Exosat at the moment. Yeah, so there's work ongoing in that direction. I think it's a very interesting discussion looking to Athena. Yeah, just how far can you get in making things that people can use more directly. Yeah. But that often blows up in the data space a lot. I mean, a lot of the data we will get from Euclid and so on is not because the satellite produces so much. It produces much, but what you get out of it after it's been processed, that's what fills those enormous amounts of terabytes or Euclid. Okay.
Okay.
Thanks.
Thank you, Peter. And I think with that, we are almost reaching the hour. Unless there is one last very pressing and very quick question. Don't see any hands raised. Well, let's thank Norbert again for his wisdom on XMM planning strategy. And let's hope that things, oh, there is a hand raised. Oh, for some reason they keep going up and down. Okay. Okay, I can't see anybody now. So as I was saying, let's hope all this wisdom gets transmitted to Athena and we have as much success as XMM-Newton or more, hopefully.